David Joseph Bohm was born on December 20th, 1917, in Wilkes-Barre, Pennsylvania, a coal mining town in the heart of America's industrial heartland. His father, Samuel Bohm, was a Jewish immigrant from Hungary who owned a furniture store. His mother, Frieda, struggled with mental illness throughout David's childhood, a shadow that hung over the family and profoundly affected young David. The household was not happy. Samuel was often absent, focused on his business, while Frieda's condition deteriorated. David grew up feeling isolated, different, questioning the conventional assumptions that others accepted without thought. This sense of being an outsider, of seeing things differently, would define his entire life. From an early age, Bohm was drawn to deep questions. He wasn't just curious about how things worked, he wanted to understand the fundamental nature of reality. Why did things exist? What was the relationship between thought and matter? What was consciousness? These weren't typical concerns for a boy in a Pennsylvania coal town, but Bohm couldn't stop thinking about them. He read voraciously, science, philosophy, anything that addressed the big questions. His father wanted him to take over the furniture business, but David had no interest in commerce. He wanted to understand the universe. In 1939, Bohm enrolled at Pennsylvania State College to study science. He was a brilliant student, but also a difficult one, always questioning, always pushing back against received wisdom, always asking, but why? In a way that professors found either fascinating or annoying. He majored in physics and showed exceptional mathematical ability, but what really set him apart was his conceptual thinking. He didn't just want to calculate, he wanted to understand what the calculations meant, what they revealed about the nature of reality. This philosophical bent, combined with his technical skill, made him stand out. After completing his undergraduate degree, Bohm moved to the University of California, Berkeley, for graduate work in physics. He arrived in 1941, just as World War II was engulfing the world, and as theoretical physics was grappling with the implications of quantum mechanics. Berkeley was one of the centers of American physics, home to J. Robert Oppenheimer, who would become Bohm's doctoral advisor. Oppenheimer recognized Bohm's talent immediately. Here was someone who could not only solve difficult problems, but could think deeply about their meaning. Bohm worked on theoretical physics, contributing to early plasma physics and quantum theory. But his time at Berkeley would be complicated by politics, by war, and by his growing involvement in leftist causes that would eventually destroy his American career. At Berkeley in the early 1940s, Bohm became involved in radical politics. He joined organizations sympathetic to communism, attended meetings, signed petitions. This wasn't unusual. Many intellectuals in the 1930s and 1940s were attracted to leftist politics, seeing communism as a bulwark against fascism and a solution to economic inequality. Bohm was an idealist, concerned about social justice, opposed to fascism, and naive about the darker realities of Stalinism. His political activities seemed harmless, discussion groups, theoretical debates about economic systems, but they would haunt him for decades. Bohm's doctoral research focused on plasma physics, the study of ionized gases, crucial for understanding phenomena from lightning to stars. His work was brilliant. He developed a theory of plasma oscillations and collective behavior, showing how individual particles in a plasma don't act independently, but organize themselves into coherent collective motions. This work on plasmas would later influence his thinking about quantum mechanics, the idea that apparently separate particles might actually be part of a larger, interconnected whole. He completed his PhD in 1943 with a dissertation that made significant contributions to plasma theory and would influence the field for decades. But then came a cruel twist. The Manhattan Project, the secret effort to build an atomic bomb, was ramping up, and Berkeley was deeply involved. Oppenheimer had been appointed scientific director and was recruiting the best physicists. Bohm's work was relevant to the project, and he naturally would have been included, but because of his leftist associations, he was denied security clearance. He couldn't work on the Manhattan Project, couldn't access his own doctoral dissertation, which had been classified, and couldn't even discuss his research with his former colleagues. it was a bitter exclusion. Here was one of the brightest young physicists in America, shut out of the most important scientific project of the era because of political associations he'd made as an idealistic graduate student. Bohm spent the war years teaching at Princeton, working on whatever unclassified research he could pursue, and feeling increasingly alienated from mainstream American society. When the war ended, and the atomic bombs had been dropped on Hiroshima and Nagasaki, Bohm was troubled by the moral implications. He had wanted to contribute to defeating fascism, but now he wondered about the unleashed forces of nuclear weapons. His political views became more complex, less dogmatic, but also more suspect in the emerging Cold War climate. In 1947, he joined the faculty at Princeton University, one of the world's leading centers for theoretical physics. It should have been the beginning of a brilliant career. Instead, it was the prelude to disaster. At Princeton, Bohm threw himself into teaching and research. In 1951, he published Quantum Theory, a textbook that became an instant classic. The book was remarkable for its clarity and depth. Bohm had a gift for explaining complex ideas in ways that revealed their conceptual structure. He presented quantum mechanics in its orthodox Copenhagen interpretation, explaining wave functions, the uncertainty principle, measurement and collapse, all with exceptional lucidity. The book was praised by everyone, including Einstein, who was also at Princeton. Einstein read it carefully and told Bohm, "You have explained quantum mechanics better than anyone, but the theory itself is still wrong." This conversation with Einstein was transformative for Bohm. Einstein had spent decades arguing that quantum mechanics was incomplete, that there must be a deeper reality beneath the probabilistic quantum formalism. He famously said, "God does not play dice," expressing his conviction that the universe must be deterministic at its deepest level. Most physicists had dismissed Einstein's concerns. Quantum mechanics worked, made accurate predictions, and the Copenhagen interpretation, however strange, was the accepted view. But talking with Einstein, Bohm began to wonder. He had written the best textbook on orthodox quantum mechanics, yet he found himself increasingly uncomfortable with the theory's implications. Was reality really probabilistic and observer-dependent, or was there something deeper, some hidden level of reality that quantum mechanics didn't capture? But before Bohm could pursue these questions, his world collapsed. In 1949, the House Un-American Activities Committee, HUAC, began investigating alleged communist infiltration of American institutions. Bohm was called to testify in 1949. He invoked the Fifth Amendment, refusing to answer questions about his political associations or to name others who had been involved in leftist organizations. This was an act of principle. Bohm wouldn't inform on his friends, but it had consequences. He was arrested for contempt of Congress, though later acquitted. But Princeton, unwilling to be associated with someone accused of communist sympathies, suspended him and then refused to renew his contract. Suddenly, at age 33, having just published a landmark textbook, David Bohm was unemployable in American academia. Universities wouldn't hire him, government labs wouldn't consider him, colleagues avoided him for fear of guilt by association. This was the height of McCarthyism, when accusation was treated as proof and political associations could destroy careers. Bohm was devastated. He had done nothing wrong, his political activities had been mild, his scientific work was apolitical and excellent, yet he was being treated as a traitor. In 1951, facing unemployment and continued persecution, Bohm made a painful decision. He would leave America. He accepted a position at the University of São Paulo in Brazil, going into what would become a permanent exile. In Brazil, isolated from the mainstream physics community, struggling with a new language and culture, and deeply depressed by his exile, Bohm did something unexpected. He revolutionized quantum mechanics. The conversations with Einstein had planted a seed, and now, with time to think deeply without the distractions of American academic politics, Bohm began working on an alternative interpretation of quantum theory. In 1952, he published 2 papers that shook the foundations of quantum mechanics: a complete deterministic interpretation, now known as Bohmian mechanics or pilot wave theory, that reproduced all the predictions of quantum mechanics while restoring determinism and objective reality. Bohm's theory was radical. He proposed that particles always have definite positions and follow definite trajectories, unlike in the Copenhagen interpretation, where particles don't have positions until measured. But these particles are guided by a quantum potential derived from the wave function, a kind of information field that influences particle motion. The wave function isn't just a mathematical tool for calculating probabilities. It's a real physical field guiding real particles. When you measure a particle's position, you're not causing the wave function to collapse or creating reality through observation. You're simply learning what was already there. The particle was always in a definite place. You just didn't know where. The beauty of Bohm's theory was that it made exactly the same predictions as orthodox quantum mechanics for any experiment you could actually perform. It wasn't some fringe theory with different predictions that could be tested and rejected. It was empirically equivalent to Copenhagen. But conceptually, it was completely different. It restored determinism, eliminated observer dependence, and provided a clear picture of what's happening at the quantum level. Bohm thought he had solved the quantum measurement problem, had shown that Einstein was right to be uncomfortable with Copenhagen, and had provided a more satisfying foundation for quantum theory. The response from the physics community was overwhelmingly negative. Oppenheimer, Bohm's former advisor, dismissed it contemptuously, reportedly saying Bohm's theory was juvenile and refusing to allow it to be discussed at Princeton. Most physicists simply ignored it. Some attacked it as a desperate attempt to restore classical determinism, a backward step away from the profound insights of quantum mechanics. The timing didn't help. Bohm was a pariah, exiled for political reasons, and his controversial interpretation only made him more radioactive. A few physicists, including Einstein, found Bohm's work interesting, though Einstein thought it still didn't go far enough. But for the most part, Bohmian mechanics was dismissed and forgotten. Bohm was crushed. He had done groundbreaking work, had shown that an alternative to Copenhagen was possible, had potentially solved deep conceptual problems in quantum theory, and no one cared. The exile continued. After Brazil, he moved to Israel in 1955, then to England in 1957, where he finally found a relatively stable position at Birkbeck College, University of London. But he remained on the margins of the physics community, his work on hidden variables largely ignored. His name associated with political controversy and heterodox views. It seemed his contributions would be forgotten. But Bohm didn't give up. If the physics community wouldn't accept his hidden variables theory, he would go deeper, think more radically, develop a completely new way of understanding reality. In the 1960s and 1970s, Bohm developed his concept of the implicate order, a philosophical and physical framework that challenged the most basic assumptions of Western science. He argued that conventional physics, with its focus on isolated particles and separate objects, was looking at reality in the wrong way. The fragmented, divided view of nature was a useful approximation for many purposes, but it missed something essential. Bohm proposed that reality is fundamentally undivided. There are no truly separate objects, no absolute boundaries between things. What we perceive as separate particles or distinct objects are actually abstractions from a deeper, unified whole. He called this deeper reality the implicate order. Implicate meaning enfolded or folded inward. In the implicate order, everything is connected to everything else, not through forces or fields in ordinary space, but through a more fundamental connectivity that transcends space and time. The explicate order, the world of separate objects we perceive, is just one way this implicate order unfolds or expresses itself, like waves on the ocean are expressions of the deeper water. This wasn't just philosophy. Bohm developed mathematical models of the implicate order and tried to show how quantum mechanics could emerge from this deeper level. He used the analogy of a hologram. If you cut a holographic image in half, each piece contains the whole image, just with less resolution. Similarly, in the implicate order, each part contains information about the whole. This holographic principle, as Bohm called it, suggested a radically different way of thinking about part and whole, about information and reality. In later years, physicists studying quantum gravity and string theory would propose similar ideas, though usually without acknowledging Bohm's prior work. Bohm also explored the relationship between consciousness and matter. He argued that thought itself is a physical process, creating structures in consciousness just as surely as physical processes create structures in matter. More radically, he suggested that consciousness and matter might be different aspects of the same underlying reality, that the separation between mind and matter is another false division. In his book Wholeness and the Implicate Order, 1980 and later works, Bohm developed these ideas, drawing on quantum mechanics, relativity, philosophy, and even Eastern mysticism to present a unified vision of reality. Many mainstream physicists dismissed Bohm's later work as too speculative, too philosophical, not really physics at all. But others found it profound and inspiring. Bohm developed a following among physicists interested in foundations, among philosophers of science, and among seekers looking for a more holistic worldview. He gave lectures, participated in dialogues. He was particularly interested in dialogue as a way of exploring ideas collectively, and corresponded with thinkers from various fields. He met and had extensive conversations with the Indian philosopher Jiddu Krishnamurti, exploring the relationship between thought, reality, and consciousness. These conversations, published in several books, revealed Bohm's deep engagement with questions that went far beyond conventional physics. David Bohm died on October 27, 1992, in London, at age 74, just months after being elected a Fellow of the Royal Society, a prestigious honor that came decades later than it should have. He died feeling that his major contributions had been largely unrecognized, that his exile and political persecution had prevented him from achieving what he might have achieved. But even before his death, things were beginning to change. A new generation of physicists, less dogmatic about the Copenhagen interpretation, was rediscovering Bohmian mechanics and recognizing its value. In the 1980s and especially the 1990s, interest in alternative interpretations of quantum mechanics surged. The measurement problem, how does the probabilistic wave function become a definite outcome when we measure, remained unsolved in orthodox quantum mechanics. Physicists began taking Bohm's hidden variables theory seriously, realizing that it provided a clear, consistent alternative to Copenhagen. Papers were published developing Bohmian mechanics further, applying it to new problems, exploring its implications. By the 2000s, Bohmian mechanics was a respectable minority interpretation, taught in some quantum mechanics courses and discussed in Foundations of Physics conferences. Today, Bohmian mechanics is recognized as one of several viable interpretations of quantum mechanics, alongside Copenhagen, many worlds, consistent histories, and others. It's particularly valued for its clarity. It gives a definite answer to what's happening at the quantum level, with particles always having positions and following trajectories. It's used in quantum chemistry calculations, in understanding quantum tunneling, in analyzing the double-slit experiment. The quantum potential that Bohm introduced has been explored in various contexts. And increasingly, physicists appreciate that Bohm was asking the right questions about what quantum mechanics really tells us about reality. Bohm's later work on the implicate order and wholeness, while still controversial, has influenced thinking in several areas. The holographic principle has become important in quantum gravity and string theory, where physicists propose that information about a volume of space can be encoded on its boundary, a holographic relationship. Quantum entanglement, which Einstein called spooky action at a distance, and which troubled him deeply, is now recognized as fundamental to quantum mechanics, and Bohm's emphasis on the interconnectedness of quantum systems seems prescient. His ideas about the relationship between consciousness and matter have influenced discussions in philosophy of mind and even in some interpretations of quantum mechanics that give consciousness a role. Perhaps most importantly, Bohm's career illustrates the dangers of scientific orthodoxy and political persecution. His hidden variables theory was dismissed in the 1950s not primarily because of scientific arguments, but because of Bohm's political status and the dominance of Copenhagen orthodoxy. Good ideas were rejected because of who proposed them and because they challenged received wisdom. This is a cautionary tale about how science can be distorted by non-scientific factors, politics, personalities, institutional inertia. Bohm's eventual vindication, even if partial and posthumous, demonstrates that scientific truth has a way of emerging eventually, but also shows how much time and talent can be wasted by prejudice and orthodoxy. Bohm's textbook, Quantum Theory, remains in print and is still used by students. His papers on plasma physics are foundational to the field. His hidden variables interpretation is taught and discussed. His ideas about wholeness and the implicate order continue to inspire physicists, philosophers, and seekers looking for a more unified understanding of reality. And his personal story of exile, persecution, intellectual courage, and eventual recognition stands as a reminder that great scientists aren't always recognized in their time, that descent from orthodoxy can be valuable even when it's uncomfortable, and that physics is done by human beings whose lives and ideas are shaped by forces beyond the equations. David Bohm spent much of his life as an exile, exiled from his country for his politics, exiled from mainstream physics for his heterodox views, exiled even from full recognition of his contributions until late in life. But exile gave him a unique perspective, freed from the constraints of orthodoxy, able to think thoughts that others didn't dare think. From that exile, he proposed an alternative quantum mechanics, developed a vision of reality as undivided wholeness, and asked questions about consciousness and matter that we're still grappling with today. The hidden variables he postulated might not be the final answer to quantum mechanics mysteries, but they showed that alternatives exist, that the Copenhagen interpretation isn't inevitable, that reality might be richer and stranger than even quantum mechanics reveals. That insight, born from exile and vindicated after death, is David Bohm's lasting gift to physics and to our understanding of the quantum world that underlies everything we see, touch, and experience.